Hello everyone, welcome to lecture 2. I intently set the title of lecture 2 as quantifying transmission because here we'll be learning about the fundamental building blocks of detection theory. So as you know, our sequence will be starting from detection theory, and then after detection we will be estimating it. That's how generally things are done. First, I need to detect a signal to be able to estimate its parameters, right? So in that way, we'll be detecting it first. We'll be developing different models for detection for the purpose of detecting signals. So we'll be starting with a very simple case today. But before that, let's look at the entire scenario in a very simplistic manner. So for example, we have a source. So a source produces six signals. Okay. So there are two statements because here we are primarily considering a binary detection scenario. As I have discussed in the first lecture in the introduction, there can be multiple hypotheses, or there can be only like the classification can be binary classification. So here this is a binary detection scenario. Because this is a binary detection scenario, there are two cases. We represent mathematically, we denote this by hypothesis. Okay. So we denote it by H naught and H1. So H naught is an observation where the source does not send the signal or the signal is absent. This is also called as null hypothesis. Okay. In the academic terminologies, it's called as null hypothesis. Null hypothesis usually we can set it to anything, but usually we set it to what is absent or what is not present in the negative connotation. That's how we use the null hypothesis. And H1, which implies that the signal that the source or the transmitter sends is H1. I mean the alternate hypothesis. That means the signal is present. Okay, that is the alternate hypothesis. These are the academic terms. So you will be crossing these terms again and again in this entire course. So what happens? There is a source which produces either of the outputs. Either it does not produce anything, which is a null hypothesis, and it produces a signal, which we can represent by an alternate hypothesis. Now there is a probabilistic transmission mechanism. Okay, here is a mechanism. It can be very simple and it can be very complex as well. So in the simplistic case, there is 1.5 chance, like there is half chance. There's a probability of 0.5 that the signal goes through. There's a 0.5 chance the signal does not go through. So a probabilistic transmission mechanism is a setup because any kind of transmission we do, we cannot guarantee that it is being transmitted every time in the perfect possible way. There are always cases where it can be missed, where the source, the system tries to send a signal, but it does not get sent, and vice versa. That is the only reason we are studying detection theory. If our machines were 100% perfect without any kind of issues, then there would be no necessity for this theory to be built up. Okay. Now, when probabilistic transmission happens, the entire transmission we can divide it into two spaces. So this is an observation space. An observation space consists of all the possible observations. Okay. Because this is a binary detection scenario, we have the observation space divided into two parts. The first part we define as R0 or Z0. So basically the observation space R0 denotes that there is no signal that is observed. Remember, there is something called as transmitted and there is something called as observed. Okay, this is transmission and this is observation. Okay, so it is possible that a signal might be transmitted, but we don't get to observe it. Okay, so this is very important. This distinction needs to be kept in mind. So we have here R0, we represent the observation space as no signal. And if we do observe one, so we would put that observation into the space R1. Okay, that means that yes, the signal is observed. Now, because these two observation spaces are totally independent of each other, this is our assumption. in this binary detection scenario, these are independent of each other. That means that if a signal is not observed, that does not affect the probability of the signal being observed. Okay, so these are completely independent, non-overlapping. And the other thing is these two are mutually exclusive sets. That means the possibility of one happening itself decides the possibility of the other happening. I mean to say, if I observe that there is no signal, that is absolutely implied that in that specific observation, if I don't observe a signal, that means a signal is not there. So these are mutually exclusive as well. So it can be represented mathematically as, because there are two observations and those are independent and mutually exclusive, we can have that R naught intersection R1 is equal to phi and R naught union R1 is equal to the entire observation set. Okay, I hope this is clear. Having said that, having set up the system of how the source transmits H naught, but it is possible, transmits H naught means the signal is not being sent, but it is possible through this probabilistic transmission mechanism, which is a black box, we can get an observation H1. It is very much possible that we get the signal in the observation space. And it is also possible that the source sends the signal H1, but we end up not receiving it. Okay. So this is what I'm trying to set in. For the purpose of quantification, taking it mathematically. So if I don't send any signal, there is always a possibility that the sent signal is just a noise, just a random noise. That's what we try to model here. In the very simplistic scenario, we know the probability distribution of the observations of the hypothesis being made. So for example, we have an observation X naught. X naught is a single sample. You might observe it. We have discrete set of observations. So we kind of represent one sample of it by X0. Okay. So that means the first sample. Now, let us assume that this is a white Gaussian noise. Okay, this is just a Gaussian noise. We know the probability distribution. This is a normal distribution which has a mean 0 and the variance to be 1. This is our first assumption. To start building the model, to get the understanding, to get the feeling of it, this is our first assumption, and we shall be taking it throughout the entire lecture. Okay, I think this part is clear. We are just assuming that we have an observation which is a Gaussian noise, which is a pure Gaussian noise, which means there is no signal. Okay, now because there is no signal and this is just white Gaussian noise, let us assume it to be under hypothesis H naught, or the null hypothesis. That means there is no signal. Okay. And in the very simplistic case, and in the simplest of cases, let us assume when there is a signal, when we want to represent the alternate hypothesis, let us assume that we have a signal along with the noise. Because practically this is always the case, right? It is not possible that your receiver does not receive anything because there is so much noise around. So the receiver is bound to catch noise. You cannot make a noise-free receiver which does not receive noise. It will receive, but you can filter it out. So here is our hypothesis H1. Okay, that is given by, we have a noise and the signal is also sent along with it. Now the signal is a simple DC noise, not a DC noise, I'm sorry, it's a DC signal. A DC signal, it can be voltage, it can be current, it can be anything we are observing, does not matter, but its amplitude is 1. Okay, that means we have a 1 amplitude, a DC signal. Okay, so I think there is no doubt as to why we are assuming this. This is the null hypothesis where there is no signal. No signal is implied by just Gaussian noise. And we have the hypothesis H1, which means that there is a signal. The signal is there. The signal is detected. That is represented by our observation. That is the noise plus signal. Okay. We would be modeling this right now. So as I said, this omega 0 is said to be Gaussian noise. Now this is a Gaussian distribution, of course, with a mean of 0 and a variance of 1. So this particular curve, this particular curve is representative of that. See here, this is mean 0. The mean of this distribution is 0 and the variance is 1. We can assume it to be so. Okay. And see how it is represented. This is probability of the observation where we have the hypothesis H naught. Okay. This notation, subtle notations are very important. Okay. We have that we are given, we have the hypothesis H naught. Under the hypothesis H naught, we have the probability distribution of our observation. Okay, this is probability of observation under hypothesis H naught. Okay, similarly, see, because we have an amplitude, a shifted observation shifted by 1, so our entire distribution is shifted right by one unit, and this is representative of our signal. Okay, so this is represented by, so because this probability distribution is actually under the hypothesis H1, this is also a Gaussian one, but shifted by 1. The mean is shifted by 1. The variance remains the same. Okay, this is not the only scenario. This is the most simple scenario, the simplistic case to kind of develop a framework, to develop our understanding. Okay, I hope I'm able to make you absolutely clear about what I want to speak here. Okay, now let's proceed to trying to detect the signal. Given the hypothesis, if you want to detect a very basic detector, you see, just by geometry, because you have ideal like the same Gaussian distributions in both the hypothesis, just mean shifted by 1. So both of them can be said to meet at 0.5. Okay. So now we would try to see, like, if the probability of our observation somehow turns up to be greater than 0.5, that means under this region where the probability is greater than 0.5, you can see that the dominating probability of observation is under hypothesis H1. The probability of observation under hypothesis H1 dominates the probability of the hypothesis of the observation under hypothesis H0. You see here H0 recedes and H1 kind of increases. So a very basic detector would be when we have the probability of observation to be greater than 0.5. When the observation we make is greater than 0.5, we can say that with some sense of certainty, we can say that the signal was sent. We can say that the observation belongs to the hypothesis H1. And just in the reverse scenario, if we go to, if we see that the observation is below 0.5, if x0 is below 0.5, that means the probability distribution under hypothesis H0 is dominating the curve. Okay, and you can see that here the probability under H1, this is receding. So basically we can say with much certainty that the hypothesis H0 is true. That means the signal was not sent. Now once again there are gray areas possible here. Because of that, the detection is necessary. If it was an absolute, then this entire theory would be completely rubbished. This entire theory would be totally redundant. There would be no point in building such a theory. It is simply because of this area that the entire theory of detection is built. It is to handle this area. Okay. So in a very simple manner, you see, this is kind of our decision region. Okay. We can tell this to be our decision boundary, because this is a boundary that helps us take decision. So when we go greater than 0.5, when the observation is greater than 0.5, we can tell that this entire region comes in the R1. Okay, we have the observation space R1 under this region. Similarly, if we have the observation to be below 0.5, we can say that this entire region below 0.5 will be our observation space R0, will fall under observation space R0. Okay, is that clear? So I think trying to explain it with the help of probability is clear up to now. Okay, so what we did here, we built a very basic detector here. a very basic detector where we have defined certain terms as to what is the threshold, what is the boundary beyond which we can comfortably say that, okay, this is very much possible that we'll have a hypothesis if this exceeds a value, and if it does not exceed a value, then the hypothesis H naught is true. Once again, this is not a fixed threshold. We just built a detector out of our own, you can say, common sense. The threshold, you can keep it here. The threshold, you can keep it here. It depends. It really depends on the situation. Okay. There is no one-stop solution to the threshold. It depends on many things, as we'll be seeing in the upcoming lectures. So basically, we built a detector where we have a threshold, and two sides of the threshold are the two decisions that are being made. Okay. Now with that, let's come to the gray area. Let's come to defining the gray area. Okay. So because we are talking in probabilistic terms that the hypothesis H1 is true, the hypothesis H1, H naught is true, there is always a possibility that you will have cases where, for example, the signal was transmitted but it was not detected, and vice versa. These regions are called by specific names. These are errors, obviously. So these are called as type 1 error and type 2 error. Just hold on a minute. We shall be discussing it in great detail. So you see, if this is our decision boundary, okay, we can say mostly that there is a probability that here we have hypothesis H1, this PDF, this probability distribution functions is a representative of the observation under hypothesis H1. So we can say with a fair grade of certainty that we have the signal being sent here. But here is a region. There is always a possibility. There is always a possibility that the observation comes under the H naught, the P of X naught, where hypothesis H naught is given to be under this. So for example, it is always possible that we detect a signal, but there was no signal sent at the first place. Okay. Are you getting this point? I have the PDF, I have the probability distribution of this curve. This entire curve represents that the signal was not sent. This entire curve is a representative of the fact that signal was not sent. So part of this curve is also representative of the fact that the signal was not sent. But at the same time, as we have the threshold here to be 0.5, greater than that, 0.5 greater than that, we have this entire region. I have shaded it by red. Now here is where we detect, because we have said that if it exceeds 0.5, we will say that the signal is detected. But there is a chance that the signal was not sent, but still it was detected. This is called as false alarm. Okay, now why this name false alarm? You must understand this is during the World War. For example, we want to detect a fighter plane or a missile or any such component. We suddenly detect it. Okay, but we recheck it and we see that it is not there. That comes under false alarm. Although that's rare, we can assign our limit to it, our tolerance to it. But this is the entire scenario, as you can see. So this is represented by P of Fa. Now, what is probability of false alarm? It is the probability that the signal was not sent, but it was detected. In a refined terminology, we can say that when H naught is true, but it is rejected. That means the signal was not sent, H naught is true, but it is rejected. That means we detect a signal. Okay. Similarly, we can have something where we send a signal. We do send a signal, but we don't get it. So we do send a signal. This PDF is the representative of hypothesis H1, which says that we send a signal. But at the same time, if we have our observation to be less than 0.5, there is a chance that it will fall under this region, although a slight chance, but some chance that it will fall in this region. You see, the entire region here is not bothered. We are only bothered about this specific yellow shaded region. This is the place where this PDF comes under hypothesis H1, that means the signal was sent, but we won't be able to detect it. Okay. So, because it is below our given threshold that we have taken. So this can be called as type 2 error, or it is called as miss. Okay. We tell it by miss. This is very obvious, right? We missed the detection. It was there, but we could not detect it. We missed it. That's why it's called as miss. So it can be represented as p miss. This is very significant. Okay. So if there are errors in detecting, what can we comment about, like in general, about what is the probability of detection? So it is very obvious, right? If we do not miss, we detect. So we can say that the entire probability we have here, right? So if we don't miss it, we detect it. So if we kind of remove this area from our distribution under H1, given H1, the entire area that we are left with can be the probability of detection. So if we have this entire area, this will be detection, because this is the threshold beyond which we are detecting 0.5. Okay. So this is the entire region of detection. These are some of the terminologies. I took so much time in just trying to explain this because it will serve as very important part, especially when we'll be trying to uh, set up the quantitative formulation of these definitions that we are dealing with right now. Okay. So there are two types of error, type 1 error and type 2 error. Type 1 is when H naught is true, but it is rejected. And type 2 is when H1 is true, but it is rejected. Okay. So we respectively call them probability of false alarm or miss. Okay. Now let's take this particular formulation into the terminology of mathematics, because just saying when H naught is true and it is rejected, PFA does not mean anything until we can calculate what PFA is, the probability of false alarm, PFA is. So let's try to build the mathematical notion around that. This is important. So for example, when we talked about PA, if you remember from the last slide, this part is the PA, right? So if we want to represent it in the mathematical terminology, so we have the probability distribution function. See, PFI is always with the PDF, the probability distribution function under hypothesis H naught. Okay. So we have this hypothesis and we integrate it. But where we integrate it in the observation space R1, this is very important. That means in this case, it is 0.5 to infinity. Okay. In this case, don't mistake it as a general mathematical formulation. So this, if you understand the previous slide, what I explained in the previous slide, this will be very trivial, very obvious. Okay. We have the probability distribution here. We integrate it, but the region is set on R1. Okay. This is the false alarm. We can also represent it by the probability of detecting hypothesis H1 given that H naught was sent. Okay. That means we detected that the signal is there when there was no signal. This is another representation of this. So it can be represented with this integration, because we'll be solving problems. Developing this formulation will be very important. So I want you to pay utmost amount of attention to this. Similarly, we have P miss here. So when we miss, what really happens? That the signal was sent, but we could not detect it. So basically the signal was sent. This is the PDF of the signal being sent. So if we try to integrate the area where we have the decision region, the observation space R naught from the decision region, we would be calling it that we have missed the detection, or the entire probability of miss can be represented by an integration of the PDF under hypothesis H1, where H1 was sent, but we received H0. I mean that we could not detect a signal, but signal was actually sent. That's when we missed it. Okay. This is the type 1 error and this is the type 2 error. So now I guess that you have, I would rather hope that you have a proper mathematical formulation of what it means. I took time to explain this because of this very reason. I would expect you to sit with this and try to explain to yourself why this is the case, because this limits and this PDF will be very necessary when we'll be jumping into problems. This concept will be again and again coming into play. That time I won't be explaining why it is like this. Okay, that's why this particular lecture. Okay. Summarizing all of what we learned today, there is an equivalence of terminology that is there. So the null hypothesis, or the H not in this case, we can tell that it is just noise. There is nothing. And if there is a signal with noise, now without noise there cannot be any receiving. There would be noise. There is bound to be noise. So we can call that as an alternate hypothesis. Type 1 error is called false alarm. Type 2 error is called miss. Then the probability of false alarm is represented by alpha, or it is also called the level of significance. Okay. Sometimes you can have this term, level of significance. You should be able to understand what it is. Probability of type 2 error is beta, and it can be represented as P of miss. We are missing it. Okay. So this can also be called as beta. And you obviously know 1 minus beta is 1 minus P miss, which is the probability of detection, which we learned in the previous slide. Now see why it is called the power of the test. Because the greater we have the probability of detection, the better our classifier is, the more powerful our classifier is. So we set up a test and we want to decide the power of its test. We can estimate it by the probability of detection. How much is it? The more we have PD, the more power we can tell of our particular detector. Okay, so this region can be called as false alarm, this or type 1 error. This region can be called as type 2 error, and this entire region can be called as the probability of detection, that is 1 minus probability of miss. Okay, so let's keep our lecture up to this today. In the next class, we shall be starting to set up certain criteria to build good detectors. We'll be starting with the Neiman-Pearson criteria, the NP criteria of detection. Okay. So I hope you have the entire concept at hand here, how we decided to have a source and it sends signal. But because of various intricacies, the signal might get distorted. The signal might not get sent. We might not detect, or the signal could be sent and when we're observing it, so we have an observation space, which is where the two events are independent and mutually exclusive of one another. After that, we try to build a detector out of our common sense by deciding a threshold which appeal to our logic, and after that we carried out that logic to establish some particular terminology which we'll be using again and again: false alarm, miss, probability of detection. Okay, the PDFs under hypothesis, under both the hypothesis represented by semicolon, probability of observation under the hypothesis, respective hypothesis, we have the PDF. How this is done? It is shifted by one simply because we have the simplest of situation where we have a Gaussian noise, and we have the signal as a DC signal of one unit. It can voltage, it can be current, like whatever that is. Okay, so that's pretty much it about this lecture. See you in the next lecture. Thank you very much.